Hello everyone, today I want to explain my homework 2.a. EMG signal processing. The presentation will follow this structure, starting with the homework objective, a brief introduction to EMG, then the hardware setup, followed by a step-by-step workthrough of the single processing code, and finally a summary of the result and the conclusions. This primary goal of this homework is to process EMG signals to identify specific activities or states. Specifically, we need to simulink an EMG signal, apply filter and other processing technique, and then visualize the results to clearly identify properties of muscle activity. Before diving into the code, let's briefly review what EMG is. EMG is the technique of recording the electrical activity of muscle. It's widely used in clinical setting, sports sensor, and even for control processions. As we will see, the raw signal is quite noisy, which is why processing is intuitive. For this assignment, we used a simulated signal. However, in a real-world scenario, we would need hardware like EMG electrode, a data acquisition system such as an Arduino, and a computer for processing. The electrodes are placed on the muscle connected to the DAQ, which then sends the data to the computer for analysis. Step 1 is signal generation. The code creates a simulated EMG signal by combining parts of random noise, representing muscle activity, and quieter parts representing resist. And we can see in the plot the result in a raw signal with two distinct brackets of activity, which we will process in the following steps. Step 2 involves bandpass filter. We apply a fourth-order Butterworth filter with a passband of 20 to 450 Hz. This filter removes low-frequency drift and high-frequency noise, leaving us with a clear signal that better responds to the actual muscle activity, as shown in the plot. Step 3 is verification. We take an absolute value of the filtered signal, which converts our negative value to positive. This step is critical because we are interested in the magnitude of the muscle activity, not its direction, and it prepares the signal for envelope extraction. Step 4a is envelope actuation using a 3 Hz low-pass filter. This smoothes the reflected signal correctly, giving us a clear envelope that represents the overall muscle activity level. As we can see, the two bursting of activity are now represented as two boards. Smooth parking, making it very easy to identify when the muscle was active. For calculation, step 4b, use a 40 Hz low-pass filter. This results in the less smooth envelope that retains more of the high-frequency components from the reflected signal, while it still shows the two activity paths. It noisier and provides more detailed information about the rapid changes in muscle activity intersects. In conclusion, we followed a standard EMG processing pimply, starting with the raw signal, applying bandpass filter, rectification, and finally low-pass filter to extricate the environment. Results clearly show that we can successfully identify periods of muscle activity from the simulated signal. The choice of the low-pass filter's cutoff frequency is a key fundamental that balance between a smooth, easily interpretable envelope and one that retains more detailed dynamic information. Let's look at this video. This is my patient code. Thanks for your listening. This is all my homework 2.a. See you.